So it's our pleasure to introduce Monica Vazirani, who will be talking about representations of the affine BMW category.
Great, thanks. Well, thanks everyone. Can you hear me okay? Great. Thanks everyone for whatever time zones you're in for joining, and thanks very much to the organizers. It's really nice to have these great talks to focus on and enjoy, especially with the world being so crazy. And so today I'm talking about representations of the affine BMW category, but annular maybe was a slightly better word for it. And everything I'm doing is joint with Kevin Walker, who is here in the audience. And I've learned from online teaching that, you know, chalkboard brain, I have experience, but Zoom brain is like 10 times worse. So if you ask me a question, I get stuck, he might rescue me. Okay, so I'm going to talk about what is this BMW category, or the rectangular or annular or finite or affine, and how to construct some representations of it. And this construction is motivated by topological quantum field theories, TQFTs. Okay. And I used to think of it as being sort of very mysterious when it was new to me. I'm getting more on board with it. So I think for this audience, I don't really need this slide to remind you what a representation of a category is, especially because in Eva's talk, we had representations of two categories. But just to remind you, right, for each object, we associate a vector space. Okay, we're a linear category, so we can do that. And for our morphisms, we want linear maps between our vector spaces that are compatible with our composition. And this coincides very well with when you have a representation of a group. If you think about your group as a category with one object and the group elements are the morphisms, then you just have this one vector space and the elements are acting on it in such a way that you get, say, a homomorphism from your group to GLV. Okay, so now what's the category that I want to look at today? Well, let's start out with the finite or rectangular BMW category. And my objects are basically collections of n marked points in the rectangle. And actually they're framed. And what are my morphisms between them? You just connect the dots, sort of, well, not exactly however, but you can do things like so. You know, you can connect things from the top to itself, bottom to itself. For some reason in this picture, I don't have things crossing each other, but they can. All right, so these are what my morphisms look like, subject to various relations, not just isotopy. But if you have something that closes up on itself, you can just get rid of it at the expense of putting some constant delta. And for everything I'm doing today, my parameters, S, alpha, delta, and so on, are chosen generically. If you want to think of them as being specialized to generic complex numbers, you can, or you can work with them being parameters and determinants and work over a base ring or, you know, field over polynomials in them or rational functions in them. Okay, and I have various parameters and there's some relations among the parameters which you don't need to worry about. And then what if you have a little kink? Oops, that was the wrong direction. If you have a kink like so, you can straighten it at the expense of picking up one of these other constants, alpha, and that's the framing brings that into account. You know, again, these relations are for BMW. You might have seen other relations where you can just straighten at no expense, but we do have an expense here. And then we have, you know, everything's a bit thickened, so we can have overcrossings and undercrossings, and they're not the same. We're not being symmetric. And the relation is when you pick up one of your parameters and you get rid of the crossing, you can sort of, you know, straighten sort of horizontally and vertically. And you get this relation here. And I should say that my strands that are running around, they're not oriented in this picture. But everything that I'm saying would work if we chose to make them be oriented. And for instance, in the case if everything was pointing up then it wouldn't make sense to have a sort of a cup cap going, and we would just lose that from the relation, and our parameters would be slightly different in a slightly different setup. But you can make everything work. I'm just not for this talk. All right. And how do you compose morphisms? You just stack the diagrams on top of each other, and then you use isotopy, and you straighten, you wiggle, and you do what you need to do, subject to the relations above. And very often you'll get a bubble trapped in the middle that'll pick up delta. All right. And so, okay, that's just if I'm going in this picture, 5 strands on the top and 5 strands on the bottom, that's an endomorphism. And then that algebra, you might recognize it as the BMW algebra, if you're familiar with that. Let's see, well, Berman, Wenzel, Murakami, but they're alphabetical order. But I said it's a BMW category, so you don't just, you don't just have to go from 5 points to 5, you could go from 3 to 5. But because of the way the relations and everything work, you do have some kind of parity shift. You're not going to have morphisms between 4 and 3, for instance. All right, so let me, oops, hang on, I'm just getting some things synced up on my computer over here. All right, so to give you an example of what idempotents look like, for instance, in this algebra. So if you're familiar with sort of things being secretly oriented or not dealing with overcrossings being different from undercrossings, right? This might look a lot like the symmetric group. And if you were in the symmetric group, you would expect an idempotent that looked roughly like, you know, identity plus a crossing divided out by, say, 2. But instead we have these parameters and you pick up coefficients, but we do have this cup cap, and there is a contribution from there if you want to actually make this be an idempotent. Well, if you want to make these be orthogonal idempotents, okay? And of course, the cup cap with the appropriate constant there becomes an idempotent. All right, and so I started with this category, and I said that you know, we have objects and morphisms, and of course I want an idempotent complete. I want to throw these idempotents in. I want linear combinations. Okay. So, all right. Now, you might have seen pictures like this before. If you don't make a difference between over and under crossings, that just looks like, well, if you take the same number of strands on top and bottom, that's just the Brauer algebra. And you might have seen the Brauer algebra before. Where would you have seen it? Well, we had a talk, Chris Bowman was talking about Schur-Weyl duality yesterday, about the interaction in type A of representations of GLN and SD, so they don't have to be the same N. And so if you did that, say, in type B, and you said, well, what plays that role of, you know, you take the defining representation V tensor V tensor V tensor V n times, what's the centralizer algebra there? That's the Brauer algebra. And so this is a deformation of that, the Q in there. And it's only a coincidence that in type A, Sn is also the Weyl group. You don't get the type B Weyl group here, you get the Brauer algebra. Okay. So, all right, so that's sort of my finite rectangular category. And then there's this affine or annular version of it, which is instead of drawing these pictures on a rectangle, you put them on an annulus. So in other words, my marked points now live not just in a rectangle, but in an annulus. And now what do my morphisms look like? So just the way with my rectangle, I had to take kind of a top copy and a bottom copy and connect the dots. Here we take a top annulus and a bottom annulus. Well, an inner and an outer annulus, and we connect the dots. And we have all the same kind of generators we had before, like having cups or caps or cups caps on, you know, cross over and under crossings. But we get a new kind of generator, something that wraps around the annulus. Okay, and that's something that I'm gonna, you know, I would call this guy X or maybe X2 because it's on the second dot winding around. Okay, all right, and so I want to look at representations of this of either category really. Okay, and so again, I need to give you a vector space for each of the objects. And how are we going to give these vector spaces? Topologically, And then I'm going to relate them algebraically and sort of see why they're the same. Okay. So yeah, so how am I going to attach a vector space to these marked points, whether I'm talking about a rectangle or an annulus? Well, I'm going to have some manifold and some piece of its boundary that looks like a bit of rectangle or a bit of annulus, depending on which category I want to work with, and have my n marked points living on that little piece. And then my vector space is going to let tangles kind of run around all around the manifold at once, but come back and end at these n marked points. I could also have 0 marked points. And then how do I make that a representation? I just thicken that little bit, that little collar of it, and I put my cut cap there or my crossing there. And then I add and I say, that's a new collection of tangles from my old collection of tangles. And that's how I act. That's how I get a representation. Okay, and it really is a vector space. Okay. And whether it's finite dimensional, infinite dimensional, what properties it depends a bit on the manifold. Okay, and of course we do have these relations. All right. Okay. Now this construction of getting representations this way and getting some structure on them is motivated by TQFTs, topological quantum field theory. I have to apologize if you can hear the noise in the background. Today's garbage day, coming around collecting the recycling and stuff. And so what is a TQFT? To me, Kevin taught me it's a machine for turning topology into algebra. And so, whoops, wrong pen. And so I'm on board with that. And how does it do that? So if you have, well, for this dimensional TQFT, it's saying, okay, give me a 3-manifold, I give you a vector space. Just like I said, you have these tangles, these running around inside, that skein module, that is your vector space. And so it's the BMW skein module because these relations that we put in, overcrossing minus undercrossing is this linear combination of other things, or getting delta when you get rid of a bubble. We put those relations on our skeins running around. Okay. And of course, for any boundary condition, you get a vector space. So we have actually a whole family of vector spaces for our 3 manifolds. Okay, but a TQFT takes into account not just 3 manifolds, but 2 manifolds, 1 manifold, 0 manifold. It's a good TQFT. And as the dimension of the manifold goes down, the categorical complexity of what you assign goes up. So it's only a vector space for a 3 manifold, but to a surface, we actually get a linear category, like my BMW category. Okay, and we also want the algebra to respect the topology. So nice topological things you can do should be compatible with the algebra. So what do I mean by nice topological things? So, for our 3 manifold, we have these vector spaces. And for a surface, we have this category. Well, if Y is in the boundary, if the surface is in the boundary of the 3 manifold, then these vector spaces should give us a representation of the category. And so this is the idea by which we're getting representations of these categories topologically. Also, if you have a pair of surfaces, then you can think of your 3 manifold as giving a bimodule. Okay. And so this is another tool that we're going to use to construct these representations. We're actually going to take a 3 manifold, kind of cut up its boundary into, or pieces of its boundary, seeing various surfaces there, and then we're going to use this bimodule. Well, you know that when you have a bimodule, that's a great way of getting a functor from representations of one thing to the next. That is a bimodule for. Okay, and then I'm not going to actually make use of, at the moment, the fact that when you glue manifolds together along a common boundary, then that should correspond to taking a tensor product over, well, the algebraic object you associate to the boundary. But that's another important property that you have, an important structure here that I'm hoping to make use of in future projects. Okay, so now, I have to apologize. Well, those of you who've seen me talk about this before, this is fairly ancient work, though you wouldn't know from it actually like being on the archive yet or anything. And my slides are rather ancient too, and these drawings were done on some old sketchy way, and I haven't updated them. So one day maybe I will. Okay, so so this is, Kevin describes this as a one-handle construction. We started calling it the hat box construction because I'm really bad topologically, and over the phone explaining how to think of something, you know, it helps to describe it as more common things. So I was like, oh, a hat box, you know, then you have it sitting in the right way. You don't have it turned sideways. You think of it in the right orientation. Okay, so my three manifold that I'm going to take that's going to give me a bimodule and thus a functor is going to be a very boring three manifold. It's going to be a solid cylinder. Okay. And so what I want to do with my solid cylinder, I want to find interesting surfaces on the boundary. So what is the boundary of my solid cylinder? Well, I can think of, you know, I have the top of my hat box, my lid, and the bottom. And I'm actually going to think of the top and the bottom together as sort of one piece of boundary. And then what's left of the boundary is this annulus that goes around on the outside. And so having cut up this, you know, this boundary in this way, we are going to have a bimodule between top and bottom. So the top is really just a rectangle, a disk, and so is the bottom. So I have two copies of the disk. So I have sort of two copies of my finite category. And then my outside annulus, one of my affine or annular. Okay, and so this boring three manifold, this solid cylinder, gives me is going to give me a functor from give me two finite representations. I'm going to spit out an affine representation. And again, we're going to do this topologically and then match it up to the algebra. And yay, combinatorics. Okay, so and how is it going to work sort of more concretely, which is that I sort of, so my generators, again, my annular generators, I've turned everything sideways so it can kind of fit on the slide, right? I have these crosses, I have these cup caps, or just cups, or just caps, and I have these X's that wind around. And so they need to know how to act. Okay, and how are they going to act? They're going to act by, on the top of my hat box, that one copy of finite, I'm going to sort of impose a representation. Well, what would that mean? Well, I said I picked my parameters to be all nice and generic. And part of that was so that the finite category, the finite algebra, they're acting semi-simply, and I have these nice idempotents that go with my simple representations there, and I had that picture or a linear combination picture. So I can just think of, I have a boundary condition of like, put that picture sitting at the top. And the same thing for the bottom, put a finite picture, put an idempotent, put a linear combination of tangles there at the bottom. And then if I want to know, you know, how does this generator act? I put this generator at the top, I have the boundary conditions at the top, I have the boundary conditions at the bottom, and then I let my tangles run all over the place, and I see how does this act on the tangles subject to these boundary conditions. And so this is how we're getting a representation. Now let's put some notation on it. So let's call that representation, I'm going to call it M for module mu lambda n. So mu says, put the mu idempotent or the mu simple representation. It turns out these representations are parameterized by Young diagrams, so mu partition is a good name for it. Put lambda at the bottom, and then the n is my category information, right? The n is my object. The n is how many marked points I have along the annulus, okay, and giving me a representation there. So this is my representation for the object n, okay, or my whole big family. All right. And I should say, right, this was my solid cylinder three manifold. You could take much more interesting three manifolds and also do this. But even with a solid cylinder, it's interesting, I think, what we get. Okay. Yeah, so as I said, we have this functor. Okay, give me a mu at the top, lambda at the bottom. It describes a representation of my annular or my affine category. So, so let's see. We're not quite at the 25-minute mark. This is kind of a natural breaking point. Organizers, do you have any input or guidance about whether to do an early break or power on and take a break when people are actually tired?
I think it's perfectly fine right now to have a little break.
Okay, let's have our little break now, and I'll tell you, especially for people who possibly wanted to run away, that's the topology. Next, I'm launching into lots of algebra and combinatorics, and we won't see the topology again for a while.
Okay, great. So then we start back at 41.
I'm going to take a little bathroom break. I'll be right back in time for questions if any come up. Or ask Kevin questions while I'm gone.
Hi, Monica. Would you mind going back a slide to the picture with the hat box?
This one or?
Yeah, this one here, the one hand, just down there. This is where I got confused because I sort of thought, okay, I'm happy with the idea that you've put a hat box inside another hat box, and that gives you this left to right multiplication. If that. What's but so I thought that what would go in the green cylinder would be another diagram looking like a sort of strands going left to right, but then you put a diagram on the top and the bottom as well, and what's that about? That's weird to me.
Yeah, so let's see if I can try to explain it and or draw it. So the idea is, I've chosen to put, say some idempotent here, like it might be this one, right? And I've chosen something else here, which might look like, with the appropriate constants there. And I guess it doesn't even have to be the same number of strands here. I guess there could have been some extra number of strands here. And so, and then I have, let's say I want to have a representation of, 4 for the annular guy. So first of all, what do the elements of my module look like? They're just, attached strands any which way that you can that makes sense, subject to having my boundary conditions there. And so first of all, that'll be finite dimensional, which isn't necessarily obvious, but it will be. And now, so that's my vector space.
So there's a parity constraint on all 3 pieces then? There's a parity constraint?
There's a total parity constraint. Yes. Yeah, the sum of the number of boundary points everywhere should be 0 mod 2. And now, so that's my vector space. And now given my vector space, if I want to know the module structure, if I want to know, say, how this guy acts, then I just, attach it here. Whoops. I just attach it here. And then moves around the pictures and gives me some other linear combination of, say, my chosen basis that I picked. And that gives me the module structure.
Oh, okay, cool. Yeah. Sorry, I thought that the algebra was somehow had all three of these guys going on now, but okay. The central guy is the module, and then you just stack things around that, only acting on the left and right then.
Wait, say again?
So when you put another hat box around that one, you don't put anything on top and bottom.
Right, the top and the bottom are this fixed boundary condition.
Okay, cool. Thanks.
Yeah, exactly right. And now if I want to compose this and say, now how does this guy act? You know, it just kind of stacks up here.
Mm-hmm. Okay, cool.
Yeah. The one that's winding around, I don't know if my drawing skills are quite good enough to draw without it totally messing things up. But...
Okay, thanks.
Cool.
But if I can ask on this, clarify that the dots on the top, do they have to connect to the side of the cylinder, or could they go from the top to the bottom? The internal.
So, I mean, I guess I kind of think to myself, I've sort of chosen. So yeah, could they go like this way? Is that what you meant?
Yeah.
Absolutely,
Could they do that?
Yep.
Okay.
Yep, that is definitely something they could do. Mm-hmm.
In particular,
so the number of dots on the side is the number of dots on the top and the bottom minus an even number.
Correct.
Yeah.
Correct. Yeah. So there's some overall parity constraint for the sum of the number of dots.
And so
and in particular, there's no parity constraint other than all three of them.
Correct.
Okay, and so this n in your notation denotes the number on the annulus. Like the boundaries, these are like in lambda and mu kind of hidden, how many mark points you have there.
This n is these dots here. That's my n. And it has nothing to do with lambda and mu other than this overall parity constraint. Mm-hmm.
And is it true that in the boundary conditions, you encode how you want to partition the boundary so that you know that you have to take top and bottom as one part of the boundary and the rest as everything else? And you could do it differently.
Yes.
Okay.
Yeah. But for this particular bimodule and this particular functor, I've chosen exactly.
Yeah.
I should say Kevin chose it.
Okay. Thanks.
Actually, Monica, could I just make a short remark? Someone asked about gluing things onto the top and bottom. And if we want to think of it as a bimodule, then that's the other, the other half of the bimodule action will be stacking diagrams on the top and the bottom. But what Monica's emphasizing is if we want to just fix some representation for one side of the bimodule and look at the induced representation, we can do that by just imposing idempotent boundary conditions.
Yeah, I guess right. I was influenced by using the bimodule as a functor. Yeah, because with the presumption that the finite categories or the rectangular categories are easier to understand, that we do know all their representations, and it's harder to build representations of the affine or the annular. But yeah, it is a bimodule. It goes in both directions. Thanks, Kevin.
Okay, great. I think now would be a good time to continue.
All right. So to continue, I have to look ahead in my slides of where I'm going. So, all right. So what are we doing, right? We've started, right? So I've got, the top, I'm imposing basically a finite representation of the finite guy. And so that means that has a particular number of fixed points there, or your boundary component. And for the bottom, so let's say, m points on the top, L points on the bottom, a representation mu on the top, lambda on the bottom. And I'm producing a representation of the annular guy that has this input mu and lambda, but any n at all can go here, because again, I want a representation of really the category. Okay, don't worry about this X semi-simple at the moment. Okay, and you might ask yourself too, if you're familiar with similar algebras, symmetric group, Hecke algebra, do you already know a functor? Give me two representations of the symmetric group, spit out a representation of the affine symmetric group, or two representations of finite Hecke algebra. How do I spit out a representation of the affine Hecke algebra? And in fact, if I give you two simples to actually get a simple, well, or zero if the parity condition's off. Okay. And at first, when this problem was posed, I was like, I don't know of any functor like that. And then I realized I did. I just didn't know how to translate the solid cylinder bimodule into an algebraic bimodule, but it works really well. Okay, so now I had you ignore this X semi-simple word, or I guess I should say calibrated. You can, if you search for calibrated in a lot of Arun's papers, you'll turn up lots of great stuff. Okay, so what does it mean to be X semi-simple? So I have some polynomial, or I prefer Laurent polynomial subalgebra going on and acting on my module, and we'll say it's X semi-simple. Basically, if the x's are simultaneously diagonalizable, right? If I can break it up into a direct sum of weight spaces. So meaning I don't have Jordan blocks. All right. And then so, great. So you give me, a character, basically just a tuple of n non-zero numbers, and I can talk about that weight space. Okay. And one thing that's nice in this theory, when we're sitting inside the context of symmetric groups, Hecke algebras, Brauer algebras, BMW algebras, when we have these x's running around, if you have a simple representation and it's also X semi-simple, I can simultaneously diagonalize the x's, it turns out those weight spaces are either one-dimensional or zero-dimensional. And so you should contrast this to Lie theory, right? You can say, okay, I have my favorite Lie group or Lie algebra, and I have, my Cartan subalgebra and maximal torus acting semi-simply, and I have weight spaces. Isn't that lovely? But of course, you know that you get high-dimensional weight spaces there. That's not what happens here, because this subalgebra is just much bigger in relation to the rest of the algebra, okay? And having one-dimensional weight spaces means that up to some scaling, you get a distinguished basis, you get a weight basis, and that's great for combinatorics. So a great lesson to learn from combinatorics is when you have a sort of multiplicity one phenomenon, that means you get combinatorics because your choices are taken away, right? And the combinatorial structure is great. So an X semi-simple representation has really great combinatorics controlling its bases and controlling the corresponding weights, right? And in fact, one thing that's also nice about these X semi-simple representations, we have these other generators, and it says that basically, if you understand just how the x's, how this large commutative subalgebra acts, you can throw away the rest of the algebra. You've determined what your simple is, and that is like Lie theory, right? If you know the character of a representation, you know the representation. At least if it's simple, you do, right? And you might need to worry about extensions versus direct sum otherwise, but if it's simple, we know it. Okay, and so that happens here as well. Okay, and so this is the tool that we're going to use, that we used at first to understand, okay, you have this topological way of building these representations of the category or the corresponding algebras, endomorphism algebras. And how do we recognize what those representations are and then understand why they're the ones we recognize? Well, we say, let's first look at how these x's, what were the x's? Remember, the x's were, wrong pen. All right, the x's were the things that came and wrapped around the cylinder, like so. Okay, and it's pretty clear those can commute with each other if you wrap the second strand around versus the first strand around. So those are my x's. And so if you're lucky enough that those act semi-simply on your module, then you just need to look at those eigenvalues. You just need to look at those weights, and you've determined which simple it is. And then, the properties of this functor and this manifold, it told us that, yeah, you give me a simple top and bottom of my hat box, and it spits out a simple there. So once you study the weights, you know exactly what's going on with this representation. All right. And it is a fact that these modules that we produce in this way, they are X-semisimple. They have a nice basis that you can construct topologically, actually, and you can analyze it, especially with some help from looking at work of, say, Belyankova and Blanchette, and also you may be also using some work of Wenzel and Hausdorff and Fred Goodman. I saw you here, probably some of your work too. That you can see that one of these X's that wraps around the cylinder on this kind of nice basis, that it will act semi-simply. And how do you get this weight basis topologically? I'll have some kind of sketches in a bit, but it's also for people who understand the Schur-Weyl side. It's actually a very Schur-Weyl kind of basis. It really is understanding, sort of decomposing, having a module and tensoring with the defining representation again, and decomposing. All right. So, right. So once we understand the weights that we get, then we can say, I recognize those weights. I recognize those weights as occurring in other modules I've understood of the affine or the annular version of the BMW algebra. And now I can match them up and say, it is exactly this module that I expect, or this module that I can construct by purely combinatorial or algebraic means. And then because the weights match, they must be the same module. And then in hindsight, you actually can look at the bimodule of the solid cylinder and realize there's an algebraic bimodule that really gives it to you as a functor. Okay. And so this basis, this topological basis, is the spine basis. And so that Kevin Walker's done a lot of work with. All right, so to get some of the combinatorics behind it, let's go back to the basics of combinatorics. And luckily we've seen some of this in previous talks. So the very basics are, go back to the symmetric group. And if you have a partition of n, a Young diagram with n boxes, that indexes an irreducible representation. So here's a perfectly nice Young diagram or partition, whoops, right? 3 boxes in the first row, 2 in the next, all left and upper justified. And so 3, 2, I would say is a partition of 5 because 3 plus 2 is 5. All right. And okay, that's for the symmetric group. If we were actually talking about, say, the finite Hecke algebra, I could still use lambda 3, 2 to index an irreducible representation, but I might give it the name M empty up to lambda 5, meaning I've got 5 boxes or it's H5, okay? Yeah, so what's the finite Hecke algebra? Just take, over crossings minus under crossings is basically S minus S inverse times the identity. Think of your strands as being oriented. Or if you wanted the BMW algebra on 5 strands, again, we have these 5 mark points in the rectangles and we have our strands running around. Okay, and let's stick with the Hecke algebra for the moment, work our way up to the BMW algebra. So this module indexed by putting empty set at the beginning, going up to lambda in n steps. Well, we use standard Young tableau of that shape, meaning I have the shape on 5 boxes. I put the numbers 1 through 5 in, such that it's increasing across rows and increasing down columns. And it turns out there's 5 ways to do that. 5 is just a coincidence with it being the 5 boxes. All right, and these are our so-called standard Young tableau, SYT. And we know they index a basis, okay, for the symmetric group S5 or for the Hecke algebra H5. And standard Young tableau, also you can think of them as being a walk in Young's lattice of partitions from the empty set down to lambda. So here's Young's lattice of partitions, the partitions of 1 on the first row, of 2, of 3, of 4, and so on, connecting by an edge. If you were to match up their upper left corners, ask is one diagram contained in the other? Okay, and this is a picture of the representation theory of all the finite symmetric groups or Hecke algebras with induction restriction functors. These are branching rules. Okay. And so for instance, our partition 3, 2, here it sits. And each of those 5 standard Young tableaux that I drew was a recipe for walking from the root down to 3, 2. This box was labeled 1 because it was the first box I added. You know, this box down here will be labeled 4 because it's the 4th box I added. This will be labeled 5. It's the 5th box I added. Okay. So these walks in the lattice are my basis. And these walks later on, well, if I wanted, I could make a topological basis that looked like this walk later on. Okay. So, and yes, and so why does this work? A lot of it has to do with induction restriction functors and having a multiplicity 1 phenomena. All right. Now, you might also know you don't just have to have nice Young diagrams or partitions or shapes. You can have what are called skew shapes, which is if one diagram is contained in another, you can X it out, you can skew it out and be left with the complement. Okay, so that's a skew diagram. And you can make standard Young tableau on skew shapes. Still, you fill it with numbers that are increasing across rows and decreasing down columns. If there's only 3 boxes, you use 1, 2, 3. Now, what is that in terms of the lattice of partitions? You just go from the shape you skewed out down to your end shape. So this frees you from starting at the root. Instead of starting at the root empty set, you can start at a mu and end at a lambda. Okay, and that's good. Remember in our hat box, we kind of had a mu on top and a lambda on the bottom, and that's where we're heading. Okay, but you might say, well, that combinatorially doesn't look to me like a representation of the symmetric group, right? And well, or of the Hecke algebra, and it's not, at least not a simple one. But now, if you asynize, if you throw in these x's, these skew diagrams, they actually, the standard Young tableau and skew diagrams index a basis of an irreducible representation now of not the finite Hecke algebra, but the affine Hecke algebra. Okay, and in this case, for it to work, we have to be able to skew it out. So mu actually ends up being contained in lambda, and n, how big our Hecke algebra is how many boxes are left in the skew diagram. In other words, the difference of those two. All right, and so what is the affine Hecke algebra? Actually, I'm just going to skip that for now. It's not that important other than it's the finite algebra enlarged with some x's. Okay. But one thing to note is the finite Hecke algebra is a quotient of the affine. By just, you get rid of the x's, and the way you do that, you send the first x to any scalar you want, 1, or think of it as q to the 0. And in terms of the combinatorics, it means that when you have standard Young tableau of partition shape, not of skew shape, the only place the first box can go is on the main, it's on the 0 diagonal. That's the combinatorial meaning of that. And so another way of saying it is my representations for my finite Hecke algebra should all occur as representations of the affine. And so that means their basis will be skew Young tableau on what shape? Well, a straight shape skewed by the empty set. So the ones that start from the root and go down to lambda are exactly the ones that factor through this homomorphism. But what I'm saying is the affine Hecke algebra also has all of these other representations that don't just start at the root. They can start at any mu and walk down to a lambda as long as one is contained in the other. So that is somewhat well-known construction. So I said the combinatorics of the Young diagrams, or the combinatorics of these representations, should be encoded in the combinatorics of the weights. So you have these x's, and what do they have to do with the combinatorics? So it turns out the eigenvalue that xi is acting on will tell you which diagonal the box I sits at. And so that says, yes, the combinatorics of the weights of my representation are exactly the combinatorics of the skew Young tableau So it's more than just a basis, it's a weight basis, and you can read the weight off the tableau. Okay. And again, so my basis of my affine Hecke algebra indexed by mu and lambda are these n-step paths from mu to lambda. And so now you're thinking, even if it didn't look like I had a functor, at least the combinatorial data of my representation seems to line up with what I promised, which was mu and lambda are these finite representations, and somehow I'm gluing them together and getting a representation of the affine indexed by that pair with some extra conditions. All right. And so, yeah, so that the x's act combinatorially by some scalar that's given by the diagonal q is on. And how does the cross act? Something like so. Is that x? That's x inverse. Sorry about that. How does the cross act? Well, it's some linear combination of the original tableau and swapping I and I plus 1 in the tableau. Or if you will, as you're walking, as you're walking on your, as you're walking from mu down to lambda, you just at the ith and ith plus first step, you might take a little detour there, and it's a linear combination of those guys. All right, and so that you can get descriptions, for those of you who are familiar with the affine Hecke algebra, of irreducible representation look like so. Now, but this condition, as you notice, right, there was the lambda and the mu at the top and the bottom of my hat box weren't supposed to have these very rigid conditions of mu being contained in lambda. We only had this overall parity condition. So where does that, how does that mix up with things, or how does that align? Well, I could try to walk between mu and lambda, taking n steps, but not always being directed, not always going down. I could allow myself to go walk all around in the graph up and down. And so now if you do go in these up and down steps, and you say, let me consider those paths, then you can make a vector space, and you can assign weights to it by a very similar formula. And what is that a representation of? Well, that will be a representation of the BMW algebra. And that's a known representation if you see work of Arun, so the Dukram or Lanaram, using more of a Schur-Weyl duality point of view, it recovers the representations they studied there, and they have the same combinatorial structure, okay? And those were all X-semisimple. And so now, yeah, if I take n-step paths from mu to lambda, those will be a basis of, say, now my BMW algebra on sort of n strands, controlled by my mu lambda and my n. And you can see why the parity is there, because if you have to do an n-step path from mu that has m boxes and lambda that has l boxes, it won't be possible unless the parity lines up in the same way we said. Okay. And again, for the affine Hecke algebra, we have some directed something going on. We have this containment condition, but other than parity, we have independence really between the size of lambda, mu, and the n. We just have this parity condition. Okay, so let's see a bit of an example. All right, so what if I wanted to have m 1, 1, 2. So 1 is just the one box diagram, that's it. And so 2 means I have to do it in 2 steps. So I need to walk in Young's lattice from one box to one box in 2 steps. So I have 3 such paths. I can go up to the root and back. I can go down to the shape 2, or I can go down to the shape 1, 1 and back. And you'll notice, an even number of boxes there. Okay, so that is a basis of this representation, okay? And now I have to just, if I want to make it a module of the BMW algebra, I have to tell you how the cup cap and the crossing act on it. And to do that, well, I get to cheat and say, I only have to tell you how the x's act because it's X semi-simple. I only need to tell you how looping around the annulus acts. And it's cooked up so that these guys are actually a weight basis. So I just have to give you some scalars that x1 and x2 act by, and I know what this representation is. What about M113? That's 0. Parity condition can't be done. You can't take a 3-step path from the box to itself. But again, these you could go from 1, 1 to 2, right? Any 2 boxes. And this 2 here means do it in a 2-step path. So then here it's 2-dimensional. So this is what these representations look like combinatorially. And they do match up to saying, you know, in this case, kind of impose this idempotent at the top, impose this idempotent at the bottom, do the two dots on the side, and then look at your vector space and see how they act, and it's the same representation. Okay, so here's my little sketch of redoing these 3 elements of my combinatorial basis more topologically. So I had these 3 idempotents that I listed early on as an example, in the example. And so what you could do, you say, okay, I have box on this end and box on the other end. That's just one strand. And I want to have 2 outcoming dots, and I want to know how my generators are going to act. And so saying I'm sort of walking input one strand, output, and in the middle I'm imposing this empty guy is really kind of saying I'm putting this diagram in the middle, and just the way the orientations go, it really just means the picture looks like so. And so, you know, you can act here with a cross or a cap, and that's what you get. That's one of my basis vectors. And it turns out if I were to wind around the cylinder, I'll just get a scalar times that. And then my other 2 weight vectors that my x's are going to act on scalars for, you somehow want to impose this linear combination going on here, and then see how an x acts, and it'll act by some other scalar. And the same thing here, we could impose a picture, you know, turn sideways appropriately there. And that's what my basis elements look like. But in a sort of a shorthand, you can really just kind of label, right? You can, you know, label this strand with box, and it comes in, and then you kind of label this with your empty, and then you label with box. And that shorthand means in terms of the topology, draw these pictures. It means in terms of the combinatorics, do exactly what we did up here. And in terms of Schur-Weyl duality, it really means, you know, tensor with the defining representation. You have a one-dimensional homomorphism space from that to these other representations, you know, pick that and keep tensoring the defining representation and picking at each branch which representation you're walking to, given you've imposed these boundary conditions. Okay, so let's see which slides I'm gonna skip now, which are probably quite a few. So yeah, so again, this is just recreating the representations studied and studied by Leduc-Ram and Orellana-Ram. Okay, and so I'm just skipping ahead to see which other slides. So just one thing that's maybe worth pointing out is that the eigenvalues of your x's, they do keep track of whether you're going up or down. Remember, there was this, the loop-de-loop had this parameter alpha, and you'll see a contribution of alpha or alpha inverse coming on whether you're going up or down in the diagram. So the algebra does see the combinatorics there. And let's right. And then so closing remarks. So this way of building irreducible representations of the annular or the affine BMW category, you could ask, are these all the representations? And definitely not, because, well, they're X-semisimple. And we know, maybe not for the category, but at least for BMW algebras, we certainly have representations that are not X-semisimple. So we're not getting them from this construction, but these are the ones we're getting from the functor, are these nice X-semisimple ones that are sort of integral in the sense that the eigenvalues we're seeing are powers of my parameters, these S's and lambdas. Okay. Yeah, and then so other things we can do with this, but we haven't yet, put in other manifolds. This was asking, can we slice up the boundary differently? Absolutely. Okay, or can we use this bimodule in other ways? Yes. Can we glue manifolds together in a more interesting way and take advantage of this tensor product? Yes. Just haven't done it yet. And then, can we somehow use the topology to build non-X-semisimple representations? I'm not sure. I haven't had much luck with that so far, because the topology, the fact that when you can rotate things around and you want to get maybe the same idempotent out after you rotate it, they put some rigidity on this. So I'm not sure how to match the topology there. Okay, I'm out of time, so I will stop.
Thank you very much, Monica. If you could all thank Monica for her wonderful talk. And you actually have a question in the chat from Tracy Hall.
Hi, and is this Tracy Hall, who was a grad student at Berkeley?
It is, yes.
Hi.
Hi.
Hi, thanks for coming. So yeah, the kth diagonal. So if our shape looks like so, then this is the 0th diagonal. And then this one is the first diagonal, and this is the -1 diagonal, exactly. So if we go up to, yeah. Right, so for instance, if we go to, whoops, sort of this basis vector that was in the representation, and I want to know how does x1 act on it, I say, I was on the 0th diagonal here, and so I'm gonna, on this v, I'm gonna have s to the 0 because I got rid of something on the 0th diagonal, and I got rid of it, so I'll have an alpha inverse. Whereas x2 will say, right, going on the second step of my path, empty set to this box. Well, this new box lives on the 0th diagonal. So again, I'll have an s to the 0. But I added a box. So we'll have an alpha v. And so if it's a more complicated picture, that you had some thing here, and then you, I don't know, added a box there, and then you went and did stuff, your x1 would act here, let's see, 0, 1, 2. So we would get an s squared, except I think there's actually maybe an overall factor of 2 here. So it might be s to the 4th, but let's ignore that typo. And then we added, so we would an alpha. Yep. So yes, it is how far the main diagonal is 0, and then you go out by 1s in each direction.
Monica, can I ask, you made this comment about, these not being all simple modules, finite dimensional simples. But I think that Zej, Doherty, and I convinced ourselves at some point that they are all X-semisimple, simple X-semisimple models. We convinced ourselves over wine and coffee, so it's not a proof. Has anyone proved that?
Oh gosh. So, and of course the, are you also having them being sort of integral in the sense that the only eigenvalue of the x's, you're allowing powers of s's and alphas, or are you allowing different sort of, Q strings?
Yeah, we can say integral because I know how to move everything around. So.
Yeah. I don't know. I don't think I personally have proved these are all of them. I don't know that I certainly haven't read anywhere else doing it. I sort of assuming, I mean, they have to be. I mean, the fact that, you have, the Hecke, that you can filter it, right? By,
yeah, that's the idea.
Quotient, or you have a waist being how many through strands, I mean, it has to be, but yeah, I guess.
Anyway, we didn't write it down, and so if anyone does, please tell me, because that's something that I would like to refer to.
Yeah, and I guess I should mention that, you know, if it's the Hecke algebra, it's much easier to prove that you have all of them this way, because you have these nice induction restriction functors between, and with the BMW, the induction restriction functors are less well behaved because you have these subalgebras and it's not free as a module over the subalgebra, and you run into trouble there. So.
So I've got kind of maybe a dumb question. My topological picture of the affine BMW algebra and yours don't really obviously agree. So the way I picture it is, you've got a solid cylinder, and you've got a core drilled down the center of the solid cylinder, like that. Yeah. And then my xi, so then all my strands are going from the top to the bottom. And the x's are the ice strand wrapping around the core and then connecting down to the bottom again. It's a completely different picture, and I'm wondering why it's the same thing.
Oh, I see. So you would have your endpoints, instead of being on the side, you'd slide your endpoints up to the top here.
Right, and then the
that's okay. You can do that. That's fine. I mean, Kevin can correct me if I'm wrong. For the sake of this functor, for the sake of this functor, we really separated it top, bottom, and side. But just as seeing this as a module for the affine, you can slide these boundary points to be up here if you want.
Great, got it.
Yeah, sorry, Kevin, did you say? What did I talk over you?
No, I didn't say anything, but now that you've called me out, I think, you know, both Monica's picture and Fred's picture can be drawn in a square across S1. And to get between Monica's picture and Fred's picture, you just rotate the square 90 degrees. So
a question. Your generator, you like the X's where the ith strand wraps the whole way around. Does it wrap around, depending on which way you draw the picture, does it wrap around inside or outside the other strands? That's a sort of trivial question, but you have to kind of, I think, have to say which one it does. And just to sort of remark, back I think around 1990, not for the BMW, but for like a category of tangled sort of construction, I'd thought about things between annuli. And I preferred as the extra generator something that if you thought about the points being equally spaced around the annulus, it would simply be a cyclic permutation going around the annulus by one step, and then otherwise like the braid and tangled generators. Can you say anything about what that element would do?
Let's see. So let me try to answer your first question first, which is, so another way that you might like to draw these things are, you know, you kind of identify, like you unwrap your cylinder, right? And then like you sort of have your mark points here. And so you could have something that, you know, wraps around and comes back. And then to your question, I think, you know, you had a question of how does the strand wrapping around, you know, dealing with these other, you know, whether it's kind of over or under these other guys. And so when it's drawn this way, it's really easy to see that the second one wrapping around doesn't interfere at all with the first, third, and fourth. When you draw it this way, you really have to be careful. And so when things really are three-dimensional and you look at it going down this way, you're like, it's no problem. It's only when you rotate it and draw it. And so the best way, I think maybe, you know, Eric Rains kind of taught me to think of it this way, which is, you know, you pick your favorite ordering, like 1 is greater than 2 is greater than 3. And if so, the 1 strand is always going to go on top of the 2 strand. Once, and then, so for these guys to commute, if 1 is always on top of 2 is always on top of 3, then those guys will commute with each other and not interfere. So that's the first answer. And then the second one, yeah. So for instance, think maybe what you were asking was, maybe I should pick a different color for these guys in the boundary box, is, what if you had them, my topological skills. And it's too thick. Okay, let me go back to black. So yeah, so if you multiply these two together, if this is what I was sort of calling x1 and x2, then, right, so this guy will wrap around, but then the second one will also wrap around. Boom. So this guy is x1 times x2, and it's just both strands together kind of come and wrap around. And I'm not sure, is that what you meant?
No, because that if you think about the permutation from the top to the bottom is the identity permutation. So cyclic permutation.
You just, yeah, sorry, now I get it. You wanted 1 to go to 2 and then 2 to go to 1.
Yeah, like that.
Yes. Yeah, that is, that you can write as a combination of you need to use x's and crossings, but it's perfectly, and of course, if we call this guy pi, x1, x2 is going to be pi squared. But you can write pi in terms of crossings and x's. I won't write them quite the right formula now if I do it, but you do have that element. Yeah, so for instance, so I'm not as good with my BMW relations as I am actually with the Hecke algebra or even double affine Hecke algebra relations, but for that, it's well known how to get between the two presentations, whether you use shift pi and just using t's crossings, or if you use t's and x's. Yeah, there's no way to get back and forth between them.
Well, thank you.
Okay, I think I'll stop the recording now.